Okay. All right. I think we are now live. So welcome everyone to our Warsaw University Astronomical Observatory seminar series, Tuesday series, I forgot to add. And this semester, as you probably noticed, we mostly concentrate on topics related to planets, planetary discoveries, planetary studies. And today, our guest is Dr. Etienne Bachelet from Las Cumbres Observatory in sunny California. Etienne did his PhD in 2013 at the University of Toulouse, and then worked as a postdoc in Qatar, and now is in California. So Etienne clearly likes sunny places, which we envy. And Etienne is our long-term collaborator on microlensing. We share proposals, we collaborate together on various topics. And today Etienne is going to talk about his key project, Omega key project, about searching for planets and stellar remnants in the entire Milky Way automatically. Etienne.
So thank you very much, Łukasz, and I would like to thank the organizer for the invitation. That's very kind of you. So yeah, my name is Etienne Bachelet, and I'm a postdoc at Las Cumbres Observatory. And today I'm gonna describe you the Omega Key project, which intend to search for cold planets and stellar remnants in the entire Milky Way automatically. So this project is a collaboration between Las Cumbres Observatory and several institutions worldwide. I will start my talk with a quick introduction to microlensing, and I'm well aware that a lot of you are very familiar with these topics. So I will try to be brief. I will discuss what are the new potential nowadays for microlensing science, and then I will finish by describing the Omega Key project itself. So microlensing is a form of gravitational lensing, and it's a phenomena predicted by general relativity that states that if a massive body crosses the line of sight between a distant source and the Earth, then the gravity field of the lens will bend the light rays coming from the distant source. And when this occurs, this creates several images of the source. And as soon as the lens leaves the line of sight, then the phenomena stop. And we speak about microlensing because in our case, in this special case of gravitational lensing, the lensing object is often up to a few solar masses. And this create a pretty small deviation of the light rays of the order of milliarc-second angle between the images. So this phenomena was predicted by Einstein in 1936 in Science, and he says that this phenomena will be very difficult to observe. The first reason will be that you need to have an alignment between the source, the lens, and the Earth of the order of milliarc-second, which is very unlikely. And the second is the angle is actually between the images so small that you can't distinguish them with our instruments. This also state nowadays, despite you can in certain cases observe the image with interferometry, and concludes that this phenomena simply manifest by a brightening of the source, what is called B here. And this is highlighted in this graph. So when the lens getting closer to the line of sight, it starts to split the light in several images, separated by, I say again, a few milliarc-seconds, so not resolvable. But what we can see is as soon as much as the lens getting closer, the light from the source getting brighter, and when the lens leaves the line of sight, then the source getting dimmer again, creating this kind of Gaussian shape light curve typical. One thing we can know very from the light curve itself is the duration is proportional to the square root of the mass of the lens. So the most massive is your lens, the longest is the event. And we know that this is a rare phenomena, and thanks to microlensing surveys that survey the galaxy toward the galactic bulge since more than 20 years, such as Ogle or MOA, we are able to compute event rate map to know what is the frequency of this phenomena. And for example, from this paper from Piemek-Mroz in 2019 that use Ogle 4 season of microlensing, we see that the event rate is actually pretty small, as predicted by Einstein. Indeed, in this map, which is a 10 by 10 arc-minute beams, we see that we can't reach much more than, let's say, about a million, 1 in a million event per year per beam. In microlensing, we synthesize that with the optical depth, which is a probability of an event getting lens at any given time, which is called tau, and we see that this probability is about 1 in a million. So indeed, this phenomena is very rare, and you need to monitor millions of stars to catch some events. The other thing we see is that the event rate increase as the galactic latitude decrease, and this is due to the increase of stellar density. And so the more you get star, the more likely you are able to have a microlensing event. So in the lucky case that the lens hosts a planet, then when the planetary system gonna cross the line of sight, in addition to the brightening due to the host star, the planet itself can act as a small lens, and it can create a small anomaly. We refer this as a planetary anomaly. And again, this anomaly is a function of the square root of the mass of the planet. And so typical duration for Earth mass planet is about a few hours, and it can go to a few days in case the planet is a Jupiter mass planet. And we have been using this phenomena since about 20 years, and thanks to the effort of the survey team and follow-up team, we know more than 100 planets thanks to microlensing, as displayed in these two graphs. So on the left, I display the mass of planet versus the orbital distance normalized by the snow line of the system. So the snow line of the system is the distance where the water start to form ice. And what we can see is planet orbiting inside the snow line have been detected thanks to transit and radial velocity mainly, because these techniques are more sensitive to this parameter space. So thanks to transit and radial velocity, and especially with the Kepler mission, we have now a very good understanding of this parameter space, but the sensitivity of this method drop off nearly the snow line. But fortunately, microlensing and direct imaging are most sensitive to this area of the parameter space. It is clear from this diagram that the different methods are complementary. And this is especially important because we know from planetary formation scenario that the demographic of planets around snowline is very important to understand, because we believe that the core of planets form around this snowline before to migrate or to aggregate gas, etc. So it's very important to use all of this method together to have a good picture of the planetary demographic. And on the right, I display the location of planets as a function of the galactic coordinates. So this is centered on the Earth, and we can see that only microlensing so far is able to detect planets systematically at several kiloparsec from the Earth. And this is important, as I will discuss later. And we can see that most of microlensing planets have been detected towards the bulge, where again the event rate is the highest. So this is where the team focused their observation. So we can use the same planets that I display to find that 70% of known planets have been detected around FG key star. This is due to some bias of observation, but this main sequence star represents only 15% of all the stars. And also 95% of this planet have been found at less than 1 parsec from the Earth. And again, this is due to observational bias. So this create question, does this create bias in our understanding of planet? There is some evidence that it could be, because we know that the planetary occurrence is a function of the host metallicity. And because there is a gradient in metallicity into the galactic, in the galaxy, so the metallicity decreases with the radius, it might be that the planetary occurrence is not the same all around the galaxy. But microlensing is sensitive to whole length type at whole distance, so it's a formidable tool to study this potential bias. And actually, this method will be used by the Roman space mission to conduct a microlensing survey toward the galactic center. So on the right, I display the expected field of view of Roman, which is about 100 times bigger than Hubble, which is a small square in the middle. We can expect more than 1,500 cold planets detected with Roman, and several free-floating planets. So the subjects are planets that traveling alone in the Milky Way, and they are predicted by a formation scenario, but they are very difficult to observe. So obtaining constraint of the subject is of first importance to our understanding of formation process. And on the left, I display the prediction from Penny et al. Of the planet population after the completion of the Roman survey. And we can see that we can expect a similar revolution as Kepler did for hot planets, but with Roman. And when these two missions will be finished, we're going to have a good understanding of the demographic of hot and cold planets. But because microlensing, you don't need to measure flux coming from the lens to study the lensing object. In fact, microlensing is very sensitive to stellar remnants. And here I display an example published by Łukasz in 2016. And we can see that this event is likely due to stellar remnants, heavy stellar remnants, because first, the Einstein time scale is very long. It's about 600 days. And we can see on this light curve also wobble, which are due to the rotation of the Earth around the sun. And this is a way to measure what we call the microlensing parallax. But I will come back to this later in this talk. Again, Łukasz using the few candidates coming from Ogles, coupled with the proper motion from Gaia, was able to put constraint on the mass of these stellar candidates. And it seems that microlensing is a very good technique to complement our understanding of stellar remnants, because it seems to cover a parameter space that is not very reached by other techniques, such as LIGO-VIGO, gravitational wave black hole and neutron star, but as well as X-ray binary black holes. So it seems microlensing is able to find candidates in this mass gap. So maybe this mass gap is not real, but we're gonna need more detection to confirm this. In 2010, Sartor et al. Published a study that claims that 30% of events with an Einstein timescale of more than 100 days towards a galactic bulge should be due to a black hole. And but Ogle and Moa survey the bulge since 20 years, and here I present the distribution of Einstein timescale from more than 4,000 Ogle events published by Rose et al. In 2017. And we can see that they found several dozens of events with a timescale more than 100 days. But this distribution is actually well fitted just by a stellar population. So this coupled with a firm detection, with no firm detection of a single mass black hole, make me think, where are they? Where are these black holes predicted by theories that we can't see? Well, one way to explain it is in microlensing, we don't measure straight the mass and distance of the lens. So we have a mass distance degeneracy. And here I try to summarize the equation we use to determine the mass and distance of the lens ML and DL. So to obtain the mass of this lens, we need at least we need to use two of this relation. And so we need to observe several observables, such as P, which is the microlensing parallax. So to do so, we can use the annual parallax if the event duration is a significant fraction of the Earth's rotation, orbital rotation period. So typically event with T higher than 30 days. Or we can use, we can observe the event from two separated places, one from the Earth, the other one from a spacecraft. This is called the space-based parallax, and it has been done several times using Spitzer and Gaia, for example. The second observable we can have is θe, the angular Einstein radius. This can be obtained if the light curve display what we call final source effect, where the magnification is flattened due to the finite size of the source. So this can be obtained in some case, but not often. The other solution is astrometric microlensing, which I will come back soon, later. And the other observable are the lens source relative proper motion and the lens flux if it's bright. And this can be obtained using high resolution imaging, for example. Because one observable which is almost always observed is T. We always have a pretty good constraint of these parameters. So the astrometric microlensing is the signature of the proper motion of the lens and source. And in fact, when this occurs, when a microlensing event occurs, you can observe a shift of the light centroid of the image. This is what we call astrometric microlensing, and observation made by Gaia will offer a large fraction of events with astrometric microlensing. We can expect that 15% mass precision for event with a baseline brighter than 15 for a lens mass of 10 solar mass. And here on the right, I display a plot made by Chris Rybicki in 2018 that shows a centroid shift as a function of time, and typical astrometric shift as order of milliarc seconds. So you really need a very good precision in your astrometry. And so Gaia is perfect for this. So using Gaia astrometric coupled with photometric light curve, we should be able to obtain handful of black hole candidates when we're gonna be able to have the astrometric time series from Gaia. But in fact, Gaia is one of several new potential for microlensing. So here I list a few, such as ZTF, Assassin, and Tomo and Gozen. So all of this all-sky survey detects a lot of transient every night, including microlensing. So this unlocks the potential of detection microlensing in the entire Milky Way, contrary to the classic microlensing surveys that focus toward the galactic bulge, again to maximize the science, the number of microlensing events. And this will be especially true with LSST. In fact, a study made by Sadijan and Poleski in 2019 suggests that LST will detect thousands of microlensing across the Milky Way every year. So on this graph, I display the logarithmic number of events as a function of galactic coordinates. So it is neat that microlensing will be detected with LSST, but all of the surveys suffer from the same caveats. While they observe a very large portion of the sky, they observe it with a relatively low cadence. And to highlight this, I present the first year observing pattern from ZTF. And we can see that the cadence of ZTF is at maximum about 1 point per day for his most dense fields. So this is clearly not enough to catch a planetary anomaly and to be able to characterize it very good, but also to obtain a strong constraint on the microlensing model itself. So while this survey offers a formidable potential to detect microlensing in the entire sky, they're going to need additional follow-up to obtain very strong constraint on the lens itself. So to highlight some recent result with this kind of event in the disk, I display first the Kojima 1LB event, which was found by Mr. Kojima, an amateur astronomer in Japan. And thanks to the early alerts, we were able to trigger photometric follow-up and catch this planetary anomaly on the peak, which was due to cold Neptune orbiting a lens located at 500 parsec from the Earth towards the Taurus constellation. The second example is Gaia 19B LD. Again, a dense photometric follow-up have been ensured, and we catch final source effect on the peak. And coupled with spectroscopy, we were able to confirm the measure from interferometry, because this event was so bright, it was possible to trigger VLT Pioneer to measure, to detect the image, the rotating image during the peak of the event, and all of the study converge to 1.1 solar mass length at 5.5 kiloparsec. So now I will present the Omega Key project. So the goal of the Omega Key project is to ensure a dense and dense photometric and spectroscopic follow-up of this promising event in the entire sky. So this is a collaboration between LCO and the University of Heidelberg, Warsaw, the University of San Sebastian, the University of Tokyo, Caltech, and the University of St. Andrews. And it relies mainly on the use of the LCO telescope network, but it's also a project part of the AEON project, which I will describe later. So this project started in the 1st July of this year, and it's currently ongoing for 3 years. So here I give a bit more details about the LCO network itself. So the LCO network is a network of robotic telescope across the world, which is fully automated and scheduled in an automated way, which means if you want to observe a star, you enter this its coordinates and observing specification, and the scheduler gonna figure out what is the more suited site to collect your observation. So the LCO network is composed of 1040 centimeters, which are equipped with S-big cameras, which are about 29 by 19 arc-minutes with 0.6 arc-second resolution. It is equipped with 10 different filters. The backbone of LCO is made of 11 1-meter telescope. On this telescope, there is 4 NRES spectrograph. So this spectrograph have high resolution optical Echelle spectrograph, which are have a resolution of 53,000. And their goal is to reach a precision of 3 meters per second for target brighter than V brighter than 11. And so they are specially designed to make a radial velocity follow-up of test candidates. But this 1 meter, they are also equipped with sinistral cameras, which are 26 by 26 arc-minutes at 0.39 resolution, and equipped with more than 20 filters. Finally, LCO is also made of 2 meters, one in Hawaii, one in Siding Spring, so in Australia. They are both equipped with low resolution Floyd spectrographs with about 500 in the optical. The 2 meter in Siding Spring is equipped with one spectral imager, which is a 10 by 10 arc-minute at 0.3 arc-second per pixels. And the 2 meter in Hawaii have recently been upgraded with a new Muscat instrument, Muscat 3 generation. So Muscat is a 4 simultaneous imager with SDSS G, R, Y, and Z. It's a 10 by 10 arc-minutes at 0.27 arc-second per pixels. So now I will go a bit aside and describe what is the AEON project. AEON project is a project led by Gemini, Observatory, the SWORD telescope, and LCO to build a rapid, flexible, and programmable access world-class to telescopes. And the goal is to create a common ecosystem and network of telescope capable of triggering observation in a synchronous manner. And it's specially designed toward LSST to be able to obtain observation from different aperture class of targets of interest at the same time. And this collaboration is now welcoming more partners. And so the key project have access to some of the time of this observatory. So now I will describe more the strategy of the Omega Key project. So it is mainly composed by two main parts. The first one is a regular photometric follow-up of this microlensing event. It is main in SDSS I and G band with several modes. The first one is regular. We try to follow each event of interest with a minimum cadence of 1 punch per day roughly. The exact cadence is scaled as with the event time scale. But as soon as the event start to get more interesting in the sense that the planetary sensitivity increase, we switch to a priority mode, which is a 30-minute cadence for the next 3 days. And finally, we have the last mode when an anomaly is detected in the light curve. Then we trigger a very intensive follow-up for the next 48 hours. The spectroscopy is intended to have at least 2 fluid spectra, if possible, and NRS spectra when the target getting bright enough. So contrary to bulge event, where we have a good understanding, or at least a better understanding of the absorption and extinction, we need spectroscopy for this event for several reasons. The first one is to eliminate false candidates. So here I take an example of a spectra we took for this ZTF AAY-BKBM event, and we can clearly see an H-alpha emission in the fluid spectra, which is a signature that this event is probably not microlensing, but more likely BE star, which is a common source of contaminants. The second goal of spectroscopy is to obtain, to estimate the spectral type of the source. So here I take the example we have with Gaia 19 BLD, where we use VLT spectra on the left and NRS spectra on the right, and we obtain strong constraint on the source type, which is in this case red giant. And the last bit, as I said previously, in the disk, the absorption is not as well known as towards the bulge. So we can use spectra to estimate the absorption as well as the source angular radius, which is important to obtain constraint on the Einstein ring radius. So the backbone of the Omega Key project is the microlensing observing platform. So this is this platform that ensure most of the work automatically, and in fact it's mainly a combination of Thumb Toolkit database deployed on an Amazon Web Server cloud architecture. So Thumb Toolkit is a suite of software developed by LCO to help scientists in their observing strategy to efficiently schedule their observation, and it's totally open source, and it can be used by anyone. It's a Python-based Django database tool. So the first task of MOP is to harvest events from the various surveys I mentioned before. So this includes ZTF, Gaia, Assassin, but also the classic microlensing surveys such as Ogle and MOA. So it's harvest all events and new photometry to cadence of about once a day using cron job. And we are currently building similar tools for the LSST data flow. So we build tools to extract microlensing event from what we call broker. such as Antares, Think, and LRC. So these brokers, they are special to develop for LSST to classify in real time all of the alerts that LSST gonna detect in real time. The second task of MOP is to fit all events in real time to obtain the event characteristics. So to do so, you use the PyNima software and take benefits of the Amazon cloud service, because we can request as many CPU as we want when we need. It's a very, very flexible and robust architecture. And as soon as the event parameters fit are done, we can use them to derive what we call the type priority, which is an adaptation of Dominic et al. And Undermark et al. Formula. So based on this type priority and other event parameters, we are able to rank and submit observation as needed. So the MOP system currently automatically submit observation towards the LCO network. And we are currently building similar tools towards the AON facilities. So here is an example of MOP in action, where this Gaia 2001 AHR event has been triggered the 16th of January of this year. And this event was harvested into the MOP system 1 day later. And after the fit was done, automatic observation was triggered. And in fact, we were able to collect our first image from Siding Spring 4 hours after MOP was aware of this event. The last bit of MOP, which is currently under construction, is to ingest real-time photometry. So the idea is MOP will submit extra observation as needed. And as soon as this observation is completed, the data are available to the LCO archive in about 15 minutes. So after the shutter is closed, so this data, they are already preprocessed like flag cleaning, etc. after 15 minutes of the shutter closure. So we can download and reduce this data using our new DIA pipeline called Python DIA. And the idea will be to ingest the real-time photometry back to MOP to let the system readjust its fits and potentially resubmit observation on the same target as the type priority change. Now to conclude, I will present some early result of the Omega project. So the first one is Gaia 20 BOF. So we can see that the Omega Key project trigger observation to complement Gaia observation. And our data clearly show a kind of plateau at the peak of the event. And in fact, this plateau is probably due to a binary lens with a mass ratio of 4%. Therefore, this event is likely due to a lens composed of a star with a brown dwarf or a planet companion. So this is an ongoing study, but this is probably the first Gaia planetary candidate, as far as I'm aware. Another interesting result is Gaia 19 DKE, where you see a very long duration event coupled with a parallax signature. So this event could be a stellar remnant lens, but the study is ongoing. So we collect photometry, and we still do. And as well, we collect spectra that confirm that the source is a star rather than any other contaminants. So given this, we'd like to thank you all for the invitation again, and I will take any question.
Excellent. Thank you, Etienne. I'll do the clapping on behalf of everyone.
Thank you.
Questions to Etienne. If you want to ask a question, please raise your Zoom hand so that I can see it here in the participants list, and then I will let you say this is a good question. Pavel first, and then Marius.
Okay, so me first. Thanks, Etienne, for nice presentation. I have a question about the MOP platform you have presented. Is it possible to download the data from LCO automatically? I mean, after the requesting of new observations, is it possible to download the data automatically and reduce it in also automatically and presenting the data in the MOP platform after that?
You mean kind of this slide I present here?
Yeah.
So no, the reduction will be done separately and in an internal server at LCO. So we will download the data, run our pipeline on it, and when the light curve will be obtained, we will ingest the light curve itself to the MOP. And I know that is not currently possible, but very soon there will be tools to download the photometry directly and programmatically from the MOP itself.
Okay, I see. So after
and for the image, yes, you can download the image programmatically if you're interested. This is we do that all the time at LCO.
Okay, but after the observations, where the observations are done, you have only the information that some kind of notification in the MOP platform that the observations are done, and you can download the data, right?
No, we have kind of listeners of the LCO archive that tell us programmatically, this new image from your project is arrived, and as soon as we receive this information, we trigger our download. We don't use currently the information on the on the MOP platform that the observation is complete. We do that separately.
Okay, I see.
But you can use that. Yes, that's correct.
Okay, yeah. I just asked because we are wondering how to do this regarding our black hole Tom, which is similar platform, as you know.
I understand, and I'm happy to discuss this later with you and Rach.
Okay, thanks.
Marius.
Okay, hello, Etienne. I'm particularly interested in Gaia 19 decay. It was on your presentation on one of the last slide.
Yes.
Yes. Oh, yes. And okay, it is somewhere on this light cover. Yes, due to this scattering with data point, can you speculate that maybe it is due to some possibility of planetary system on this event or no?
So as far as I know, this event is well explained by a point source, point length model with just parallax. There is no signs of planetary anomaly really, and I think with the Occam razor argument, we're going to choose the simplest solution, which is likely a single lens event. But I'm not currently leading this study, so I didn't see all the data. But so far as I know, this is my interpretation of this event.
Okay, thank you, Etienne.
Welcome.
Any more questions to Etienne? I might have a quick comment. You showed the timescale distribution from Przemek Muru's paper, and actually that curve, the red curve shown there, the curve does include black hole population. So it's not like,
does it?
Yeah, it does. So this is the whole broad population of all possible sources, but it's very much spread, and it's based on some assumption on the mass distribution. But the black holes are there. There was a similar plot, I think, in Sumi original paper, where he actually showed the individual contributions. So we can see that the longest ones contribute to the black hole population. So they are there, but the problem remains. The problem is still valid, that we cannot distinguish them easily, right?
Yeah.
So that point is still valid. Yeah. Okay. Any more questions? If not, then thank you, Etienne. Thank you for this enlightening talk and keeping it brief, so we stay more focused. Thanks for this. Thanks for joining us from California. Enjoy your morning. And
thank you very much for the invitation.
Thank you. And to all of you, thank you for joining, and see you next week.
Okay, bye-bye. Thank you.